Sorry?
So on Telegram.
There's a link on Telegram for?
Download
No, I haven't posted it on Telegram, but I'll do it afterwards on the meetup, okay? So basically, what I would like to go over today is build on what we did last week, and that was that we introduced the very basic fundamentals for machine learning and trees, decision trees. So what I'll go to is like more advanced trees, and then we can actually start building our own trees and try to solve some classification problems. So let's get started. So basically, full screen control function. 9, control, command, shift F, command, shift.
Okay, so on Jupyter is sorry. What's full screen?
I thought it was like F11 or something.
Full screen?
Yeah?
Command Shift F, is that what I said?
We're trying that.
Command?
Keep going.
Okay.
Command Alt.
Guys, view.
Oh, there you go.
Oh yeah, you're right.
Command 1, 2, 3, yeah, okay, cool. Okay, so basically in the previous session, we introduced our main API, which is sci-kit learn. And within it, we had predictors, which basically are models which offer a fit and a predict, as well as transformers, which offer a fit and a transform or a fit transform. So to start off, what I'm going to like to do is actually going to load some data, and then I want you to load the similar data. So what I first here now is I'm going to code this part, explain what I'll do, then I'm going to open another notebook for you guys, and you can have a go and actually try this out. So what we're going to do, we're going to load the Titanic dataset. So this is the similar dataset that we used last week. So to do that, it's going to be quite easy. So I'm just going to do that for now. I'm going to import pandas, which is basically import pandas. I'm going to give it an alias, which is PD. And after I do that, what I can do is I'm going to call pd.read_CSV, and I can do tab, which allows me to autocomplete. And you should be able, if you loaded this using GitHub, there should be a folder called 00_data, and within it there'll be titanic.csv. So if you do that, it actually fired off. So I'm just going to give it a nice alias, our name, and I'm also going to wait a second, that one. I'm also going to load. So it's actually this one, titanic.x, and then I'm going to load my target, which is going to be this. So it's going to be that for now, pd.read_csv, that 00 data titanic.y. So now I'll
Typo now.
yeah.
.csv.
Oh, here.
And the original one.
So the Y is actually the target, whether a person survived, yes or no. So what I'm going to do now is just basically, I'm going to put them inside of my two variables there. So in my case, my X is going to be basically within my machine learning problem is going to be df Titanic. I'm going to wrap this into an array. And my Y is going to be same thing, mp.array and df Titanic.target. So, and just one more thing, I'm just going to also store it for further reference. I'm just going to call this survived. So I've just added another column to my original data frame. Sorry, MP, okay, so MP basically previously is another package, which is NumPy, and this allows me to, so this is a data frame. So it has all the structure, it has basically a table kind of format, whereas mp.array, like that, breaks it down into a different structure, which would be that of an array. So this is the same data, but as an array format. So now I'm just going to save it like this. So basically now what happens is I have the F Titanic as a data frame. I have the F Titanic target as well as a data frame as a target. I have my X, which is the same thing as before, but instead of a data frame as an array, and I have my Y. Okay, now one last thing. Since we're going to be doing machine learning, we're going to actually take this data now and split it into a training and a testing data set. So we're going to use the training to train our model, and then once we get some results, we're going to compare this to the testing data set. So we're going to take the data and split it into a percentage. So scikit-learn offers a very nice function for that, and that's basically going to be from scikit-learn. I'm going to import model selection. I'm going to import train test split. So sorry for that. Yeah. So if I open up the documentation for this, actually you can say that it splits arrays or matrices into a random subset. So it's quite, if you want, you can even just copy the state example here. I've on purposely selected that my arrays are X and Y. Oh, I have it here. So basically copy and paste here. And we're going to give it like a test size of 20%. So I'm going to split my data between testing and training into 20% randomly. And what? No? No, that's fine. Wait. X is fine. Y is fine. Maybe Y dot shape. Let's see. 1308. 109. Okay, I know what happened. But no, basically, what happened was this Y does not have a header. So we need to suppress the header here. And that is, it does not have a header. So I'm going to do squeeze.to. And I'm also going to header equals none. So just going to go to the code again, close this, and happy days. So now you can see that out of the original X of shape 1309, I've created one of shape 1047 and X of test, which is 262. So it's 20% of the original. So now what I'd like you to do is, there's another data set, and I want you to actually first identify what is the X and the Y, and then do this train test split with a test size of 20% and a seed of 55. So basically what I mean by seed is, I want you to do random state equals 55. Okay, so I'll give you 5 minutes to do that. So just basically open up a new notebook and just crack on. Okay? Any questions? Okay, give you 5 minutes.
How to upload the data?
Sorry?
Using collab.research.
Okay, you need to upload. Okay, so did you download the...
Yes.
Okay, then just go.
In the collab research Google.
Yep.
You have this thing on the left, folder.
Yeah. Files. So just upload and upload into there. Yeah.
Yeah, please note the paths might be different than examples.
Okay.
Yes. If anyone needs help, please raise your hand. There are help.
Okay.
Some of us. You guys are computerists. You're okay with this?
The file is in data. 00 underscore data, sorry. So the file is in 00 underscore data. So it's 00 dot slash 00 underscore data slash Titanic. Okay?
I assume I don't see fingers on keyboards because everyone's done.
Is everyone done? Cool. So basically, I'm going to show you how it should look like.
Raise their hands if they're not.
Anyone need? Maybe they raise their hands.
If anyone's not done, please raise your hand, and we'll.
Okay. So I'm just going to basically code it out for you. So basically, again, import pandas. I'm going to say as PD. Now I'm also going to import NumPy as MP. I'm just going to load them. Then I'm just going to name them df underscore Titanic. This is going to be pd.read from CSV. And this is going to be 00 underscore data and Titanic.csv. So that means I can do that actually loaded. And now if I do head, maybe just to see a little there. Now what I want to do is that I want to do the train test split. So from scale model selection, import train test split. Now I'm just gonna do X on the, actually, I'm just gonna open up the documentation. Again, I don't want to be a bit lazy. Just copy this. So writing those out. Now, okay. So actually, if you had to look here in your data frame, we already have the survival column. So we need to actually pull that out so that we can actually put this in our Y. So that was the question too. With the X is going to be all of this information, and the Y is going to be all of this information. So I want my X to be the F Titanic. Sorry for that. The F Titanic dot drop.
The power of touch Mac keyboard.
Survival, and the Y is gonna be df Titanic dot actually survival. So, oh, this needs to be axis 1. So that means I want to drop the column. So now when I go in here, it's just a matter of test size equals 20% and random state. So the reason why I'm using random state is that you will get the same results as I am. Okay, so once again, my x.shape is 1309, my x.train .shape is 1047, and my x.test.shape is 262. Okay, everyone has this code now? And if anyone has a problem, just raise their hand and we'll just go over. Cool. All right. So last week, we introduced decision trees. And as you might recall, so basically this is the same data set. The idea behind that decision tree is that it takes your data and it builds these filters automatically, as in something that it learns. Okay, so when we say we are learning, the model is learning, it learns the optimal split between, for example, sex, whether sex is yes or no, true or false, and it automatically builds this tree for you. So the main parameters when we actually want to teach a decision tree will be how deep do I want to go. So if I want to go for deeper trees, they will explain potentially more of the data. However, the question now is how deep? How deep should I go? So let's see what this tree looks like. If I had to take a F1 score of this tree based on this data, we'd see it's 81%, which is not bad, okay? But what if now I want to test my tree between a range of depths? So I'm gonna now test the depths between 1 and 40. So literally I'm gonna try a tree which is just this deep, then I'm gonna try another tree which is 2 layers deep, 3 layers deep, 4 layers deep, etc., etc. Any suggestions of what the metric is gonna happen to it? Is it gonna increase? Is it gonna decrease? Yeah. So basically what's going to happen is the more depth we add, first it's going to explain the data, then it's going to start, actually what's happening is going to end up with overfitting. So we can't explain even more and tries to find ways of explaining what is not really there. So we just plot it out. This is what happens. So max depth, so this is the depth of the tree. So 1 depth, 2 depth, 3 depth, 4 depth. And it just then flattens out. So there's no difference if we had to use 25 or 35. So with 25 would have achieved the same performance as of 35, and possibly would have been quicker. Considering this is a small data set, we don't see the difference. But if your data set is like, I don't know, 2 million rows, it will take a while. Okay? So what I'd like you to do now is, so I'll just see this, but yeah. In fact, the problem we're seeing here is that the data is overfitting. But what we can do actually to quantify this overfitting is if we take the test data set, so that data that we're not using to train our model, and we run the F1 score on top of that, we can use that as our gauge. So what I'm plotting now is, this is the same data, but now I'm plotting also the F1 score of my test. And you see that over here, actually the F1 score of my test is decreasing. So we are overfitting, basically. The model is learning the training data set, but it's not really learning the data, realistically. It's learning quite a specific problem, which is not what we want. We want to be able to give it new data and still give us a good prediction. So what I would like you to do is, now, I would like you to actually build a decision tree classifier. So I can start it off for you here, width of max depth tree, and then the state tree. So basically, I want you to, from sklearn.tree, I want you to import decision tree classifier. In this case, I'll just call it DC, decision tree classifier. I want it to be max depth. Give it max depth tree, and then run the F1 score, which basically means from sklearn.metrics, I want to import the F1 score, and then run, you have to do first a fit here of sorts, yes, using your test data, and you need to do a predict, and then you need to score. Okay? So I'll give you like 10 minutes on this, 15 minutes, and then we can carry on. If anyone gets stuck, we're here to help you.
Having the same issue, but for some reason I don't see that. If you just hit the button there, you'll meet it. that's maybe first data, yeah? I uploaded the dummy one, like the title.
Hello? Hello? Okay. How's it going? Are you even going? Or just... Yes? Okay. Let's see. Mala. Okay. You are using cross-validation.
Yeah, I used model selection before and it didn't recognize it. So I use cross validation.
Okay. So what's the problem here? Next data is not defined. Where are you loading the decision tree? Okay, scikit-learn tree.
So we tried running this. Out file was none.
Yeah, okay. Basically, okay, you have a missing dependency for graphics, but it's fine. What I ask you to do actually is to create a separate folder, but it's okay. So what we're going to do now is let's just check something. So do you have your X? Okay, hello. Okay, so I'll just go to now exercise 2. So basically, what I asked you to do was you have an X test, so an X train and a Y train, yeah? So what I asked you to do is basically from sklearn.tree, I wanted you to import decision tree, classifier, and also from sklearn.metrics, I wanted you to import f1 underscore score. So now I'll just call it DTC, decision tree. This is the actual API, the method of decision tree. I want to give it max depth equals 3. So now there's the object, which is DTC, which is going to be a decision tree with all the parameters for you. I want to fit this to my data X train, Y train. So now this is DTC has been fitted. So although nothing happened, basically that's what happened. I mean, it's been fitted. So if you wanted to, just do DTC dot predict. And this time, instead of giving it train, I'm going to give it my X test. So now it had data which did not see, and out of that, you can see your X underscore train. So basically, this is data, sorry, test. So out of this data, so you see there's no survival rate, it was able to predict some sort of survival, yes or no. Now, how do you evaluate this? So we know that this is something that we hid from the model. So what we can do is I'm just going to call this y underscore pred. So now it exists in there. So F1 score, the y2, as you can see from the documentation, is going to be actually y underscore test, because this was never passed to the model, and pass this the prediction. So we can see that we've got a score of 75%. But now, what I'm going to do is, what if I change this to be 15? So 15, I'm just going to run this code again. You can see the actual F1 score is going down.
Was it lower?
It's getting lower. So what's happening here is actually overfitting the model. And this would explain what we are seeing here. Yeah? Somewhat flattening out, getting lower. Okay, so we need to find the best depth for a tree. Now, this was just the one parameter. We can also look at, in the case of, if we just look at trees, we also have max features, impurity, samples, and a lot more features. So one way of doing this is we can either build an array ourselves and randomly test all trees automatically, or we can just use scikit-learn, which automatically does this for us. So that's what we're going to do now. So what we're going to do now is hyperparameter tuning, which basically means we're going to identify which is the best hyperparameter for our model to explain the data. So if, for example, I want to try and find the best max depth and the best min sample split, I want to try out max depth between 5 to 30 at increments of 5, and min split from 25 to 200 at steps of 25. Just to visualize, this is the number of tests that we're looking at. So we see max depth at 5, we're going to test it first, max depth of 5, but min samples 25, 50, 75. So we have a total of what? 1, 2, 3, like 100 different, 200 different tests. I mean, just multiplication. So how can we do this? We want to also implement what is known as k-folds. So the idea here is that when we're training for these hyperparameters, we're actually not going to give all the data to the model. We're going to split the data into folds, partitions, and train different parts of the model whilst we go along. So this will, I'll show you how to do this. So within scikit-learn, what we want is we're going to do basically, we're going to do scikit-learn, same thing, model selection, but this time we're going to import grid search CV, which basically is this method which allows us to all do this combination of all possible. Yeah, so just import it. And if you want to optimize decision tree classifiers, so we have decision tree classifiers. It exists already. So this is the actual scikit-learn implementation. So what I'm going to do, I'm just going to implement it as is, as a default. Now I'm going to build my parameter grid. So how would my parameter grid look like? So if I had to do decision tree, so to open up the documentation, these are all the parameters that we can test and play around with. I'm just going to stick to max depth and min samples just for this example. So I'm going to say DTC param grid, just for the sake of argument. I'm gonna create a dictionary. I'm gonna call this max, so the actual object I want is max depth. And this time around, I want basically to use a range from 1, what was it? 5 to 30, increments of 5. So I have to just run this, so you can actually see this. And just do this, x for x in. This automatically just creates it for you. Maybe you can do this, so you can actually get the 30 as well. Okay. Now, apart from that, I also want to include min sample set. As you can see, it actually automatically suggests this for you. And this time around, I want this to be a range between 10, 110, increments of 10. So now I've created my parameter grid. It's a dictionary. So how to implement it? A very nice grid search CV. As you see, it's asking for an estimator and a parameter grid. Estimator is my DTC, which I've defined here. Parameter grid is going to be that. Now, apart from that, there's a couple of other functions that we can use. If you use CV, this is the number of times we're going to split the data and train our model. So just give it the number 3. We can also use njobs to speed it up. So this is the number of CPUs you want to use on your machine. If you do -1, it will just use all available cores. And the final thing is the actual scoring. In this case, I'm just going to call it F1. And one last thing is verbosity. I want to see my code actually spit out whilst it actually is executing. I'll give it 1, 2, or whatever. So I'm just going to name it grid equals. So now everything is defined. Nothing has been changed. Nothing has moved. Why? Because we still have to fit. That's the first. That's we always have to fit to execute something. So it's going to be a matter of grid dot fit x underscore train y underscore train. And there you go. So we're trying out 180 different possible combinations of models, and it spit out the ideal hyperparameter for you. So now this grid, which has been fitted, it actually allows us to see quite a few different options. So if you just grid dot, you can see now all these options which have the appended underscore at the end gives us the best estimator. In this case, the best estimator had a max depth of 5 and a min split sleeve of 1. Okay, it does not really make sense, not possibly because we gave it 1. It also gives us, for example, the best score. Why did it choose this to be the best score? Because it scored 80. And there's also what we can do if we actually want to see how the actual results came about. We can just do grid dot CV results. These are all the different results. I'm just going to whack them into a data frame. And you can see that these are all the different results that we did. Okay, so 60 tests. We had the main fit time, standard deviation of the fit time, the score, the actual parameters we used, and finally how they ranked within our testing. So we can also see all these results. We want to possibly QC what you're going.
Rank 1 is the best ranking?
Yeah, rank 1 would, I would say, I think so.
Actually, it's not 1, maybe it's
I think it's
more.
or the higher one.
The highest one is the best.
31, 56. I think so.
Oh, we can see the score, right, as well.
The score would, yeah, I usually just go for the, to be honest, you can just go there. This will just automatically give you the best estimator, always. Okay, so what I'd like you to do now is the following. I would like you to build your own parameter grid and actually try and identify the best decision tree. So I want you to test for max depth 5 to 25, increments of 5, samples 2, 6, 10. I want you to actually look at the documentation now for max features and set the best random state. Okay? I'll give you a couple of minutes for this, 15 minutes. I'll leave the what I'll do is I'll leave my code here, so if you want, you can copy a bit. Okay. So copy that. I'm just gonna copy this out, so everything fits in a nice one-pager for you. There you go.
We should not use the grid search or?
No, I want you to use, I want you to find the optimal decision tree classifier using grid search. So I've left the code on the page on purpose so you can just copy this across and optimize, tweak it a bit. Okay? So the parameters are between 5 to 25, increments of 5. Min samples is 2, 6, 10. Max features, I want you to look at the documentation to find what is actually available, is it a number or a string, and set the random state to be 55. Okay? Cool.
Question, so here you didn't specify max features. So it defaulted
Hello? Hello? All right. Anyone has any questions? I'm going to show you my code now. So basically, I went back to my repository, to my notebook. I'm just going to quickly code it up. So once again, from scikit-learn, model selection, import grid search, and I should have F1 score. So now it's just going to be a matter of basically grid. Actually, I can just copy across this because it was all in here. But this time, this was between 2 and 25. 5 and 25. 5 and 25, increments of 5. My max split is going to be 2, 6, 10. And then I asked you to look at the documentation for decision tree to see what's going to happen for max features, because it was set default to none. So basically, max feature takes integer, float, string, or none. So you can see that it takes all of these options. So I'm just going to do auto square root or log 2. So for my max features, I'm going to say that this is.
Why would you want to use like square root of n features?
So basically, what does square root of max features means? So how many features do you want to consider in your decision tree? So this is all explained here. So basically, if you choose to square root, that's the number of features to consider when you're looking for the best split.
Yeah, but why this specific?
So, okay, why is it log 2? Why is it square root? Well, then we need to go into the proper fundamental mathematics behind it. Like if you go too many features, then you end up overfitting. If you go less features, you don't explain what's happening. Okay, log 2 comes from, I can't remember. Log 2 and square root, basically, they did some analytical techniques to identify that it's around there, where should be the optimal number. But since we do machine learning, so we try by test, we just do auto, we can do square root, we can do log 2. That's the beauty of this. We don't need to know anything, we just test it. Yeah? And then I want my random state. I want it to be 55, so just do that. Yeah, exactly. So now if I go back to here, 55, I can just fire this off by doing this. So I'm just going to do that. Dot fit x test, x train, y train. And DTC because of the, and it's fitting 108 fits for me. Okay. There you go. Okay, cool. So let's go back to the notes. So you have to be careful now, because the more you add, the more you test, and there's a 5-fold usually. So that means the number of parameters will blow up. So what do I mean by that? Instead of testing for just 2 parameters, I'm going to test for 3. So basically now, instead of looking at just a flat single line, we're looking actually at a full-on 3D grid of different tests. So if you look at even more and more hyperparameters, you can imagine that this will just keep getting bigger, bigger, longer, and longer. So you have to be careful on what you test, basically. Okay? So what you could do is you could potentially start with a very wide grid, and then finally tune towards something that you want.
And you find it can be move or not?
What do you mean point? These are all defined based on, as you can see, this is auto square root log. Or I've defined these based on my parameter grid.
Okay.
So you choose what you want. If you want increments of 1, yes, but that means you're going to test a lot more. Okay?
for example, if you take any delay and any while for change the value, the graph it's change after or not?
The result, you mean? Yes, I mean, the more you test, the more likely we find the best parameter. But we can't, over here I'm just showing 3. Usually you test for like 7 or 8. So you'd be looking, instead of looking at 1 hour or possibly an afternoon of training, it'd be like a week of training. And if you explain it to my boss that I'd be spending a week waiting for my model to come out, he would not be happy.
Okay.
Okay?
Are there other options?
The-
Except Greek search?
Yes, there's obviously other options. There's random search, which automatically randomly picks a set of parameters and then plots them out. Or else you can also consider what is known as Bayesian search. So what Bayesian search is it starts off with a test, a random sample of parameters. Then it tweaks one of the parameters, sees the result of this change, and modifies it, basically directs to which is the ideal parameter. So it uses the information from before to get you the next set of parameters using Bayes' theorem. Okay, let's look into something next. Basically, let's look at decision trees on steroids, basically. Okay, so you understand that decision trees takes your X data and builds a tree. But what we can do is actually, instead of having one tree, what if I told you, let's build 1,000 trees and see what happens? And basically use these little small estimators to come to a massive forest of trees, average the result of all these trees to get your result. So that is basically what is known as random forests. It sounds complicated, but all it is one line in scikit-learn and just 2 extra hyperparameters. So basically, this is what random forest is. You take your data, you define, I want to create 1,000 different trees, which it will automatically create randomly, and it will just build trees all over the place for you. And then just average all the prediction to create a random forest. So this is the mathematics for anyone who's brave enough to go through it, an explanation. But realistically, we are adding n estimators, the number of trees in the forest. And if you want, you are using something beforehand, you can use what is known as a warm start. So how does it look in scikit-learn? So scikit-learn. This time we're looking at an ensemble because it's combining different trees. I'm going to import a random forest classifier. Now, RFC is equal to random forest classifier. And you can see here that there's the actual parameters, but I'm just going to fit, this time X train, Y train. So that is a fitted random forest classifier. This warning is because of the version. So we can see it's just a future warning. I'm all right with that. I'm going to predict my X underscore test. And you can see that they have a prediction as well.
Why after the bracket you put dot fit?
Okay, so if I just do this, that is now just defining that I have a random forest classifier. That's it.
Okay.
Doing that, well, I did it in one line, but to be honest, because I just changed function, I just chained functions here.
Okay, it's Pythonic.
Yeah, just be lazy instead of saying hit, yeah. So how does it look? So I'm just going to do that. RFC predict equals that. So now that goes in here, and same way as before, f1.score my one RFC pred. Actually, this is the 2. So test RFC pred. Okay, so this should be slightly better. Well, I can't find this F1 score, but this should be slightly better than the previous one. Just because this randomness allows us to not get, basically gives us the power of 1,000 small trees rather than just one tree. So now that you know this, you need to be careful as well. How many trees do I want? Should I just go for 100 trees? Should I stop at 1 tree? So this is another hyperparameter. So basically, we just whack this into our grid search and it will give us the best result. So quite straightforward there. The next exercise is meant to be you guys to code it up. But I'm going to skip this and move on to the next tree, next model. Now, this one is called extremely random trees. And that is because it's almost identical to the previous one before. But instead of just looking at random forests, so random different trees, it also takes randomness when it comes to the data. So it's randomly selecting parts of the data to build your random trees. So it adds even more options to look at. And once again, this is just mathematically, everything has been coded and everything's been tested and everything's just been wrapped inside of extra trees classifiers inside of scikit-learn. So now this is another model you can play around with. And finally, the last model we're looking into is what is known as gradient boosting trees. Now, gradient boosting trees, this is the one which is, let's say, the most intelligent one. Because the way this works is you first create a tree, okay? Then you look at what part of the data did this tree not explain. And this part of the data, you build another tree on top of it. So now you have 2 trees. So that would be iteration 2. But you don't just add it. So instead of being a plus here, what we do is we want to learn how to add. So that part is actually learned as well. The next stage is, let's see what has not been explained by the data, build another tree, and we learn how to add. So what we're doing is, and the way we learn is, we look backwards, what has not explained, and we update. So this is known as the gradient. We're calculating the gradient, identifying where we need to update, and we just go forward. So at each iteration, we add a little bit smaller trees, what are known as meta-estimators, to build our massive, big, gradient boosted trees, and we learn how we can combine these together. There's the mathematics behind it, if anyone wants to go through this. But now, we're also looking at the learning rate, which means we learn how to combine different trees, and the subsample is how we're splitting the data before we're training. Once again, within scikit-learn, this is implemented inside of ensemble. We're going to import gradient boosting classifiers, and this is now same thing, gradient boosting classifiers. So this is the beauty of scikit-learn. Everything is the same. It's just a matter of, oh, I want to load this, just plug and play. Okay, one last thing. If you're brave, this is the one which, I guess, this is what is known now as a voting classifier. So we know how to do decision trees. We know how to do random forests. We know how to do extremely random forests. And we know how to do gradient boosting trees. What if we now build a super model which combines all of these 4 together? Well, that is what a voting classifier is. So what we do is, we first train one classifier, we then train another classifier, and we then train a third classifier. Then we learn how to best combine them. And we train how to best combine them by using the data. So we can do what is known as a voting classifier with a majority voting or a hard voting. So it plainly looks at a straight up average. So in this case, 2, 2, 0, so 1, 1, 0 is going to be a 1 for sure. If it's 0, 1, 0, it has to be a 0. There's no like midway. If it's a 1, 0, 1, it has to be a 1. If I have 2 classifiers, and this time I have potentially 1, 1 has to be a 1, 0, 0 has to be 0. If I have a a split, unsure, it will always go for the smallest. That is by default. You can always change this, but this is what happens when it's by default. The other option is soft voting. And the idea here is that rather than looking at 1, 0, 1, we actually look at the probabilities behind a model being in the class. So basically, I'm going to code this up quickly for you. So what I have here, I have one classifier, which is a decision tree, one classifier, which is random forest, one classifier, which is gradient boosting. And the way this would look would be that basically, if I want to build a soft voting classifier, it's just a matter of from sci-kit learn. So let's just do this. Okay, datasets. Let's just load some couple of functions because we need this sci-kit learn datasets. Actually, just do that. Import dataset from sci-kit learn. Okay. Okay, so we're now, if we had to do this, we can see that we have a classifier, which is classifier 1, we have classifier 2, and 3, etc. So let's build this soft voting classifier. So now, from sklearn, ensemble, import voting classifier. So we have that in place. So I'm going to say VC is going to be a voting estimator for classifier. The estimators, as you can see here, are going to be, I'm just going to do that. Yep. The first one is going to be DTC, CLF1. The second one is going to be RFC, which is random forest, CLF2. And the third one is going to be gradient boosting classifier, is going to be CLF3. And what we need to do next is actually define how we want to do this voting. So the next option is going to be voting is equal to soft, if I'm not mistaken. Yep. There you go, soft. And why? Exactly, so it's that, actually. So now we have defined what is a voting classifier, combining all those three. So fit, as usual. So X train, Y train. So 2 mana values on pack, expected 2. Okay. Now about now. Okay. Maybe I need to fit this first.
For fit it for combine.
Yes, before combining them, I think I should be doing that. Let's see. Fit. How about now?
A to B, B to C. Right?
2 mana values on back. Okay, I will sort this out. But we are done. So basically, we are now able to build the best models using hyperparameters. We can look at trees, random forests, extreme random forests, and as well gradient boostings. Once we're happy with those, we just put them into a classifier to find the best way forward. Any questions? Okay. We are meant to host like a little mini competition, but we are running a bit late. So if you want to look at this, the next notebook is this one. And in this notebook, we actually prepared a little data set for you. in this data set, this is a data set which looks at what type of forest cover we have based on some data. So we are looking at, if we just load this data, we have, yeah? Yes, forest, actual trees. No, not models. What is the elevation? What is the aspect? What is the slope? Hydrology, vertical distance, like what time does we get hillside at 9 a.m. and the soil type. So you can see this was soil type 33. This was happened to be cover 2. Now we are not predicting 1 or 0, but we're predicting from 1 up till 7. So we are looking at a multi-class here. So basically, I've prepared this for you so you can understand what type of data we have. So you can see that there's hillside versus hillside. We're actually seeing different cover types coming in. The same goes to here when you compare hydrology. So actually the data shows patterns. It's not something the same. Aspect versus hillside, hillside versus hillside, noon. So you can see that actually there is something which could explain different patterns. So you can, if you wanted to, you have all the data, you have all the notebooks, you have all the knowledge now. So go ahead and predict. So what I'm showing here is basically the colors represent different forest type. So 1, 2, 3, 4, 5, 6, 7. And the only reason why I'm showing these plots is so that basically to understand, is it just some random numbers put together? Or is it actually, there's like different groups within the data, and these patterns, I can use these to find whether it is 1, 2, 3, or 7. Yes? So at the moment, this is just purely exploring. There's no prediction happening here. Okay?
But
Each point, each one of these entries here is one dot here.
okay.
I don't understand the axis. Is this like there's a mountain in the middle?
No. So basically, what I did was, I have all of this data, yes? So basically, my data frame, which is the... Yeah, I have a bunch of different columns. So basically, what I'm doing is I'm just saying I want to plot, for example, horizontal distance, one of the columns versus the other column. I'm just going to do a scatter plot of those. See, this is just a...
Position, you have distance.
Now, there's a bit of like, how did I choose these 6 to choose from? Well, then that's something else. Yeah.
It's meaningless.
Yeah, they're just too small. There's not a good correlation. Yes, it's actually there. There's the elevation. There's elevation in there. There's aspect, there's slope. So all of that is built in here.
Okay, but that's territorial. Anyway, don't worry.
This scatter does have nothing to do with actual geolocation. There's just the shapes. They just look nice.
Yeah, like what's the probability of a tree on this level of height, this far from a road to actually be at this time?
Yeah.
Something like that.
Yeah.
Without regards to actual specific location in the world.
Yeah. All right. If you have any questions, just please send them out on Meetup and we'll try to answer.
If we fit it some metrics like for Malta, the elevation of Malta,
it would not work.
will not work.
Exactly, because remember.
Thank you.
Ciao, Bjorn. Ciao. Okay, remember that basically machine learning models will never learn something which they never saw before. Okay? Thank you very much. If you have any questions?